Okay, welcome back. This is lecture 5, video 2, and we are discussing the effective number of hypotheses. Now, if you think about the application of hypotheses, we don't apply hypotheses to an abstract space, but rather to some data, right? So let's try and understand what is this effective number of hypotheses. Any hypothesis, when it's applied to data in general, what it does, right? Let's look at a very simple example in a two-dimensional space. Let's assume we have like 3 points given to us. The first point is known as x1, x2, and x3. So we have 3 points in this space, and let us assume the first hypothesis that we have is h1, and it divides the space into two parts, and it looks something like this, right? So let's say this is h1, one of the hypotheses. Now it's dividing my input space into two parts. Let's say this is the positive side and this is the negative side, assuming that this is a binary problem where you have either a +1 or a -1 as an outcome, or a yes or no, that kind of a problem. Okay, so that means this will be, according to this hypothesis h1, this is a negative, this is a negative, this is a positive, right? So all of this looks good. And before we jump into a further discussion of this, a quick reminder that in this discussion, we are only analyzing the hypothesis set. We're not worrying about the target function or the data set in terms of the training and the test. We're just trying to analyze how hypothesis sets can divide the input space, and will that be of any help to us? Okay, so having said that, let's put everything in a tabular form to understand things better. So what's happening is that this hypothesis H1 is implementing a dichotomy. Dichotomy essentially is has two outcomes, right? For example, in our case, it's a +1 or a -1. So the outcome that each of the data points takes, right, together with all the other data points is going to be like it's going to take some form depending on how the hypotheses divided the region, right? And so that's why each hypothesis implements a dichotomy in my input space. For example, x1, x2, x3, right? So in our example, x1 is negative, x2 is positive, x3 is negative, right? So this line is known as a dichotomy that has been implemented by h1. Okay, now let us assume I have another hypothesis that divides the region like this, and this is known as h2, right? So what h2 did was slightly different from what h1 did, and this one is positive according to h2, right? So this is negative according to h2, this is positive, right? Another dichotomy that was implemented by h2, and so on. So basically each line in this table is a dichotomy, and each hypothesis, the hypothesis implements a dichotomy. Okay, so what will happen is we can keep on going and keep getting like different hypotheses, and trying to figure out how each point is categorized by my hypotheses. Now we know from our knowledge of counting, right, that in this case, what will happen is eventually after, let's say, H8, like the ninth hypothesis, is going to be a repeat of one of the earlier hypotheses. How do we know that? That's because you have like three spaces to be filled. This could be +1, -1. This could be plus. So these are all the possibilities. So basically, in this case, I have 2³ total possibilities of having unique dichotomies being implemented, right? So starting from H9, I will definitely have, let's say, H2 repeat or something repeat, because the only possible unique outcomes were 8, right? So we can translate this into a more generic form where instead of like talking about only 3 points, I could be talking about 9 points in an arbitrary data set that has n points. Okay, so for example, if I have n points, which is like x1, x2, and which most likely I will have in any machine learning problem, and let's say our hypothesis h1 implements minus minus and then here plus, h2 implements something else, right, and so on. I don't know how many hypotheses are there, but they're definitely a part of this large H, which kind of represents the larger set from which we are deriving all our hypotheses, right? We can say that just like we did with 3 points, we can definitely say that the that we will have only 2 to the n unique rows in this table. So that is an upper bound on the number of hypotheses that I can have, right? 2 to the n. Because if there are n data points, at every position I can have a +1 or a -1. So basically my upper bound, so to say, is a 2 to the n rows in this table. Okay, so utilizing this knowledge here, we can define something that's known as the restriction. Let me write it down. What we can define is the restriction of the hypothesis set H to the points, whatever the data points are, x1, x2, and so on up to xn, denoted by H, x1, x2, xn, to be equal to some, like to be related to the dichotomy, such that each dichotomy is implemented by H, which belongs to my H, right? So let's say if delta is denoting my dichotomy, then this restriction is equal to the set where we implement this dichotomy, given that this dichotomy is implemented by an H that belongs to my H, right? So this is kind of giving us a restriction. Okay, so we can quantify the complexity of H on my data set x1, x2, and so on using this restrictive notation. And rather, I can write the cardinality of this restriction or the number of hypotheses based on how it relates to the data set can be bounded by 2 to the n, right? So let me write it down. Let's quantify the complexity of H on the data, which is x1, x2, and so on up to xn, using the cardinality H, x1, xn, using this restriction. So the number of dichotomies that will be implemented by the entire set will be less than or equal to 2 to the n, right? We can definitely come up with this. So this is an upper bound on the number of dichotomies that can be implemented, like the unique dichotomies that can be implemented by any H that belongs to H. Now, all of this is good, but now there is a question that arises. Now, we said that the data set or the data will be picked after we fix the hypotheses. And here we've related, or we've come up with an upper bound that is actually dependent on the data, right? So we have like a few questions to answer, which will obviously be important going forward. And obviously we need to understand how is this helpful, right? So even before we think about whether it's helpful or not, my first question would be, as I said, because like we have talked about this a lot before, what x1, x2, and xn, right, should we use to compute the complexity, because I don't know the data until I've already fixed my hypotheses, right? So to compute the complexity of a hypothesis set, that is the first question that comes in. For example, we don't know the data and we must fix the hypotheses beforehand. So that's why this question is arising. The second question, and equally important, is that is this bound for complexity? And this was, I think, even more important because we really wanted to have this thing there at least, right? So is this bound for complexity useful? Which means, is this relationship, or essentially this relationship, I'm not rewriting it. So is this relationship here, up here, is this useful or not, right? So let us try to answer these two questions. So question number one, what are these x1, x2, xn? How do we compute the complexity using them when we don't know them? Okay. So the answer to question number one is that can we compute the complexity? The question was, can we compute the complexity of hypotheses set before even looking at the data? So the short answer to that question is yes. Although we haven't seen the data, but we can come up with the worst case scenario because we understand how worst case scenarios work, and we can indeed come up with the complexity and the bound for the worst case scenario, right? We can talk about the worst case at least depending on some data of size n. What can happen when the worst case comes up for all data sets, right? So now we are going to define the complexity for like that worst case scenario, right? For the data set of size n. And that is known as the growth function. So let's do the worst case analysis. Worst case analysis. Okay, so now I'm going to define this new term, which is m of h over n. Okay, so this is the complexity possible, basically worst case for all data sets of size n, right? And h denotes the hypothesis set and n denotes my data set size, right? And this is the maximum number of dichotomies that h can implement on any data set of size n. So basically I can write it as the max over x1, x2 up to xn, and h x1, x2 up to xn. And this here is known as the growth function. Okay, so as I said, this is another way of finding the effective number of hypotheses. And from what we just saw, the maximum number, this right-hand side, the maximum number of hypotheses that can be, the maximum number of dichotomies that can be implemented by H on any data set of size n is bounded by 2 to the n, right? So which in turn tells us that we have this growth function which is bounded by 2 to the n. I'm repeating, this growth function is nothing but the worst case complexity for all possible data sets of size n. So that answers our first question, that there is a relationship and this is how we will utilize that relationship. Now, coming to question number 2, is this bound useful for is this bound for complexity useful at all? Okay, so let me remind you of something, which is our error bar. Let's look at our error bar to understand question number 2, or basically answer number 2, I would say. If you remember the error bar that related the out of sample error with the in sample error, and it looks something like this. So 1 by 2n, and then I think it was log 2, then the cardinality of h over some constant delta, right? Now, if you remember this like error bar, and now we are coming up with something that can replace this h here. Although I cannot directly replace this h and there would be some technicalities involved, but I can roughly say that if I kind of substitute my m h of n here, because that's what I'm trying to get, right? Then I'll see what happens to this error bar. So let's say if mh of n replaced this h in the error bar, n will get cancelled. Why? Because we'll have something like this. Let me show you 1 by 2 to the n, and then that is going to be log of, and let's say 2 stays as it is, and that is 2 to the n comes out, right, and gets cancelled, right? And the generalization error, which this error bar is representing, would not go to 0. No matter what we do, how large the data set is, because we have made it independent of n, right? And so it doesn't matter what size data set I bring. There is no valid relationship between E out and E in, because this, we just got rid of n. Okay. So what should we do? What do we need to do here? So basically, if you just look at this equation here, we have to come up with something here, right? Or maybe we have to come up with the value for mh of n such that that can be bounded by a polynomial, any polynomial. Let's see how that is working here. So let us again look at this. Let's say I have some polynomial, right? Log 2, and then I came up with like n to the d and then delta, right? And then if you the rest of the terms, d comes out, d comes here, and basically, if you look at like one of the terms here, it is going to be log n over n. Okay, so this is what we wanted, right? What will happen here is that if I bounded my h of n by some polynomial, then the generalization error like will tend to 0, at least as n tends to infinity. Why? Because limit of, if you just remember, this is a reminder, log n of n, especially when it is 0 as n goes to infinity, right? So if n is, basically what I'm trying to say here is that if n is really huge, if n is really big, then we can hope that we can get this error bar as small as possible, even up to 0. And that is good for us, right? Because then we are making E outcome as close to E in as possible. Okay, so in order to deal with this further, like how to do this, how to come up with a polynomial value for mh of n or a polynomial bound for mh of n, we have to begin looking at some examples first. So that's what I'm going to begin with in the next video. So see you there.